So, welcome to Chai and Why. Today, could you please turn off your phone? So, this is an example of learning. Okay. So, this is this talk is to cover Nobel Prize in Physics that was awarded very recently. Our earlier two sessions were about Nobel Prize in Chemistry and Biology. And today, to discuss and update us about what is about artificial intelligence and Nobel Prize that was awarded for that work, we have Professor Piyush Srivastava from TIFR. He is a professor at the School of Technology and Computer Science. And before coming to TIFR, he completed his BTech in Computer Science from IIT Kanpur, followed by a doctoral degree at University of California at Berkeley, and then a postdoctoral stint at Caltech. So Piyush has various research interests and hobbies. I'll not tell you that right now. So let him get on with the talk. Piyush, colleagues.
Yeah, thank you. Okay, so let me start with this. So this is going to be a talk about learning, artificial learning, learning by machines, and specifically learning by a special kind of machines. And we'll see what those machines are. But let's start the story at a different point. So I see at least some people here who might not have been born when this happened. But what is this? Does anyone recognize this headline or what happened at this point? This is from '97. Yeah, Swift and slashing computer toppers. Who was Kasparov? Yeah. What did he do? Yeah, so he's a chess player. He's by some accounts by any account one of the greatest ever. By some accounts, the greatest ever chess player, human chess player, and this was a big event. I remember like seeing this on TV. I was in I think class 5 or something at that time. Like this is in the news, in the 30-minute news that bulletin that used to come. Now, of course, you have news written all day long. And the point was that a computer had defeated a human, the best human, the best we had to offer. A computer had defeated, and not just defeated in one game, across a series of games. And this was considered a slightly, maybe at that time, okay. So initially, people thought that maybe it's a very bad thing for humanity. Okay, computers have beaten us, especially because chess, right? Chess was supposed to be like some kind of a symbolic, some kind of symbol of intellectual activity. In fact, as the Marathi word for chess is buddhibal, like strength of intelligence. That's it. No other aspect of the game is highlighted in the name. So, and that is across cultures, across several cultures in the West, in the East. Games like chess have been thought of as some kind of symbol of human intellectual capacity. And so this was a bit humbling that a machine could beat it. But again, people thought of it as fun and games. Okay, it's just one game. And chess is in some sense, if you start trying to cope with this, it is not such a complicated game. Okay, it's complicated, but it's not complicated so the point is that the number of pieces tends to go down. I mean, it does go down as the game progresses. It simplifies slowly. And then at the end, maybe the computer can just, by brute force, because it can just do these mindless calculations. So people thought it is just something like computers can multiply 50-digit numbers faster than humans. This is something like that, nothing more than that. Maybe it's fine. So then, at least at that point, one of the things that people would say that, oh, but you have this game called Go, which maybe is not as popular in India. It's more East Asian, Chinese, Japanese, and Korean game. It actually does get more complex as the game goes on. It's also similar to chess, completely a game of skill. And maybe computers will not beat that. And these kind of things, so what Deep Blue, this computer that toppled Kasparov, was doing, did look like that. So they were doing brute force. They were trying to search as many moves as possible. Human had programmed them. So it looked like, okay, humanity was still safe. And these kind of things, these brute force things, will not even get down to Go. Okay. So here is what happened about 10 years ago. So the headline is there. So AI computer wraps a 4-1 victory against human champion in Go. The human champion, I think, was DC Doll, I think Korean player. And this was by a very different kind of approach. This time, a human being had not programmed the computer to search for all the moves. There was something fundamentally different that was going on. And what was going on was that there was a computer where like there's a program where a human being had designed it, but many parts were just left blank in some sense. So some parts were just left blank for the program to figure out. Then the program played games against itself. In the beginning, it was very weak, but then slowly it started to fill in those parts where it could win against itself. At some point, it was thought that this program is good enough. Then it was put in front of the best human player at that time, or one of the best human players at that time, and it beat that human player. So it was not just brute force, it was doing some pattern recognition, some kind of things that maybe more than chess, or maybe not just calculation, but maybe some things which are sort of more, maybe one could even call them intuition. It was maybe developing things like that, possibly. So this was maybe, I mean, it was harder to cope with. It was not just, so maybe you can see that the headline has become more serious, right? So this is like some, flippant, irreverent thing. Somebody has been toppled by someone. And here it's like very matter of fact. AI computer wraps up some victory. And then it becomes more serious. This is from this year. So AlphaFold, which those of you who attend this series might have seen in the previous one. The AlphaFold is a program to predict structure of proteins. Proteins are molecules that make up our bodies, essentially. And their structures are very important. What is easier to get is what they are made of in a sequence. So they are made up of several smaller constituents. Which sequence they are made up of is easier to get experimentally. How those things are arranged in space, which is very important for the function of a protein, is much harder, much more expensive to get at experimentally, or even using a computer. And this thing, so okay, even there was this situation that sometimes humans would have intuitions that, okay, I look at some sequence and some human who has worked at it for a long time would say, oh, this structure should look like that, and sometimes would work better than a computer. This thing again, in that kind of framework, looking at several such sequences and corresponding structures, now does it better than any other computer or any human. This also won the Nobel Prize in chemistry. So at this point, you can see it has gotten even more serious, like more subdued, and like no one is talking about toppling or wrapping up or anything. It's just very matter of fact, it predicts this. So something is going on here, and this talk will be about some like a very tiny introduction to the building blocks of what has happened here. What are these programs with gaps that have achieved these things? We will never not get to anywhere close to AlphaFold or AlphaGo or any of these programs, but we'll see some smaller examples. And these examples sort of, we'll see that they actually, these ideas were there for at least 100 years. Okay. So so the current situation is this. So the point is that when you write down such a program, you want to evaluate it. Is it any good? Right? I mean, is Deep Blue any good? Yes, because it can beat the best human player. But maybe even better. Right? Maybe even if it can perform as well as a average human, that already should be a pretty good thing for a program. But this is now running into a problem because on many basic tasks, these systems are beating average human performance or even best human performance. So it's getting harder and harder to benchmark them to see whether a new program is better than the previous one or not, because the ground truth notion that we had was what a human can do, but these things are already sometimes beyond it. Okay. So this is the situation, and what has enabled these things are you might have heard this name, neural networks. We are just two examples. Don't worry about what they look like, but they basically look like some at a very high level, some small components tied into a larger block, and the small components themselves are quite simple. The whole thing might also not look too complicated, and with all this, they solve these problems. So these two are two celebrated examples. The thing on the left is called ResNet. It's from this paper. It is a network meant for recognizing images. The thing on the right hand is called Transformer. It's something meant to generate text. It's what variants of it underlie things like ChatGPT, if you use those. So we will see much simpler versions of this. That's the goal of this talk. Okay. So any questions so far? Okay. So let's proceed. So the Nobel Prize in Physics for 2024 was awarded. So the Nobel Prize comes with a citation. The citation was this: for foundational discoveries and inventions that enable machine learning learning by machines with artificial neural networks. So artificial because humans are making them. And why neural we will come to soon. So these are networks that look like the networks on the previous slide. Okay. So, so the prize was awarded to two researchers. John Hopfield has a background, it is PhD in physics, but has made seminal contributions to neuroscience and then to artificial neural networks as well. And Geoffrey Hinton, who is a computer scientist who has worked on various applications of both foundations and applications of neural networks. Okay, so so one thing I would like to say. Okay, so this is where the title comes from, learning networks. So this will be a story of. So once I have gone through these things, you might get the impression that all of these things are so simple. Why, why did it take so long? So this is a story of very simple, in hindsight, very simple ideas, and not just very simple ideas, very fundamental ideas. And one measure of how fundamental they are is that they were rediscovered and remixed by several people at several different points of time in various different contexts, in various different fields. And so one kind of analogy to keep in mind, so we are in a theater, so let's have some art also, is the one thing AI is still not good at is getting these interfaces right. Okay, yeah, so you have to keep going through. So this is not like Sistine Chapel. So the UNESCO World Heritage Committee has some selection criteria for designating a site as a World Heritage Site. And one of those criteria, the first one in fact, reads like this: to represent a masterpiece of human creative genius. One of these World Heritage Sites is the Sistine Chapel in Vatican, in Rome. It's famous for, among other things, paintings by Michelangelo, sort of a individual genius who did everything on his own, maybe with very little help from others. So this is one of those famous paintings on the walls and the ceilings of the chapel. This kind of work, the machine learning and artificial learning, is not like that. It's not the work of one or few individual geniuses. It's more like another World Heritage Site, which is closer home in Beirut or Ellora, called one of the caves. It's called Cave 16. That's a very unimaginative name. Another name is Kailash. So if you have seen this, it's a temple, two-story temple hewn out of solid rock, not a single joint, by people whose names you don't know. But you see it and you realize that this is something that is work of genius immediately. So this is like that. Several people have worked on it over a long period. This was probably done over several decades, over a long period. Many of whom maybe are not as well known as maybe they should be. But our job is to look at the structure and marvel, or try to get inspired by what has been achieved. So this will be an exercise in going through the history of where these ideas came from, and to get to some point where to how they were applied to learning. Okay. So that's the goal. Okay. So any comments, question? Yeah. Okay. So maybe I can do it right now. So why physics and why not something else? Okay, first of all, the flippant answer is there's no Nobel Prize in computer science. But the thing is that if one thinks about it, it's sort of an accident of history that the study of intelligence is not considered a part of physics. If you think about any way of defining physics, the study of the fundamental processes of nature, computation, or if you like to call it more metaphysically, intelligence is a part of that. Somehow thinking has developed in the universe. There are machines that like mammalian brains, or which do computation, which can think about abstract concepts and connect them, and at a deeper level, now slowly it's like not just in machine learning, but also so I would not go into that, but also um, in quantum physics, etc. These ideas are coming back. So computation, just like energy or mass, is like a fundamental constituent of the universe. It is not as well understood. Something that is related, that is much better understood, but still not as well understood, is information. Like how does information flow across systems? So those of you who have heard the word entropy might know that it comes up both in sort of in electrical engineering as well. One is really studying information, but the same notion carries over to statistical mechanics, which is what we'll see a little bit of that in this purpose. So I think, we should not put too many boundaries between fields, but so that is one sort of sociological answer. But the technical answer is also that computation and information should be seen as fundamental processes in nature, and this is slowly being appreciated, I think, not just at the level of award committees, but also in like scientific literature. Okay, so yeah, so let's start. So if you have seen, and I should think you should really see this. So there's some video of Richard Feynman, a very well-known physicist, about how excited people can be about magnets, and it is, if you think about it, is quite exciting. It's we come across magnets as kids, as toys, maybe in the school curriculum in around class 5 or class 6, and it is in some sense one of the most complicated objects that is there in the school science curriculum. So it has many nice features, looks magical in some sense, but one of the things that maybe we don't appreciate as well is one of the first objects we come across which has memory. Something. So I mean, of course, all of us have memory, but in the physical world, inanimate world, this is one of the first things we see which has memory. And in what sense? It has a north and a south pole. This memory sort of has persisted for a long time. That rock has had this polarity in it, and then what happens is that this memory can be altered. This is important. You might have seen things like passing current through a magnet, or hitting it with a hammer to make it lose its magnetism. So all these experiments are part of the school curriculum. So there's memory; it can be altered, and it is also somewhat robust. To alter it, you have to make an effort. You have to put in a lot of energy, hit it hard, pass a large current through it, etc. So, or large current around it. So this is so these three things are sort of special about magnets. This is not just special at a theoretical level, also at a practical level. Hard disks are basically applications of these three ideas. But what does it have to do with learning? So okay, we have something which learns, at least in this very naive sense. So what it has to do with learning is through how it was modeled. So if you think about your usual physics curriculum, Newton's equations, all of this, nothing there seems to have a lot of notion of memory. Everything is sort of time reversible. Like you can go this way, you can also go back in time. Things don't change there. Here, somehow you're seeing something where it has a notion of history. So people try to come up with simple models, simple equations, simple models which can describe such behaviors, that there should be memory. So there will be equations here. Don't get sort of annoyed by them. I'll explain everything. So what people are trying to do is to come up with very simple models. Magnets are complicated. We want to come up with some very simple toy, some small mathematical model which can have the same qualitative behavior, that it has memory. And this memory can be altered, but it is still robust to small perturbations. So these models were first proposed around 1920s by Lenz and Ising. This one is called the Ising model. It was proposed actually by Lenz. Ising solved it in so-called one dimension. We'll see what that means. So what they were trying to say is, okay, let's try to model a big magnet like this. So it's a big magnet which has some small so-called domains. Each domain is in some either one state or the other. So they are called plus or minus. Each domain is a plus or minus. And these domains are sort of, they interact with their neighboring domains. So this is some abstract representation of that. So maybe this domain interacts. So in this case, every domain interacts with every other domain. These lines represent which two domains interact. But these interactions can be sort of inhibitive or excitatory. So in the sense that a domain being plus can cause its neighboring domain to be more likely to be plus, or the other way around, can even try to inhibit it from being plus. So that is encoded by these so-called interaction parameters. So they're sort of like they're saying whether they're positive or negative. And then any such configuration of domains, the way physicists would say it, is any such configuration of domains where one domain is plus, one domain is minus, gets a so-called energy. And this energy basically depends upon how free from frustration they are. So maybe there is one domain which is asking its another neighbor to be plus, but that neighbor is actually minus. So that will contribute something to the energy. That will say that the energy increases because there is some frustration in the system. This domain wants something to happen, but it's not happening. So it might be that not everyone can be satisfied, but you want to satisfy as many of the constraints as possible. So that would be the lowest energy or the stable states. So So yeah, so that of course depends upon what the connections are, what these J's are, and the total energy is basically like the total sort of this dissatisfaction of all the domains, and you want to minimize this. So, uh, so what Ising showed is that in this, okay, so what is a system like this? So basically, then it will say that okay, the system should be likely to be in the lowest energy state. So when everyone is as little dissatisfied as possible. And then the memory would be like, what are the possible states? Are there two different kinds, two very different kinds? And are they sort of robust in the sense that if I change one of them slightly, is it that it can come back to the one I started with, or it will just go away somewhere else? So this is the kind of notion of memory. And what Ising, the reason this is called the Ising model, that Ising showed that if you arrange these domains on a line, so the only interactions are, so you put them all on a line, unlike this, and the only interaction are to your nearest neighbor. Then there is no memory. That was what he proved. It looks like a very deep statement. It is sort of a deep statement, but it's actually very easy to prove in the sense that it is now given as an exercise. If it's enough setup, I can give it to an exercise in a class 11 student and they will solve it. There's nothing very tricky going on. But at that time, the modeling was important, and he showed that there's no memory in one dimension. In fact, he conjectured there's no memory in any setup at all. And this was a bit of a crisis in statistical mechanics at that time. But this was sort of like a false alarm. Another, so Onsager, so let's not worry about this. Onsager showed that if you put it in 2 dimensions, so now you put them on a grid and everyone is connected to like their nearest neighbor. So think of it like we don't have these kind of grids in Mumbai, but in Bangalore or New York, you can have these kind of roads, right, where they cross at 90 degrees. And you only sort of, from one intersection, you only interact with the closest intersections in all 4 directions. So yeah, so this, in this kind of a situation, memory can arise. So this is what Onsager showed. Onsager is also one of the Nobel Prize in chemistry for other things, including this, but other things as well. So this is around in the 1940s, all this is going on. Nothing about learning so far, right? I have started talking about magnets for some reason. So now what does this has to do with learning? So from the magnet story, let's just remember this, that well-connected toy model of magnets. So of course, there is more connectivity in a 2D grid than in a 1-dimensional line. There are more connections. So well-connected toy models do seem to have memory. Good. So here is something else that was going on around the same time. So 43, right, 1940s. This is, by the way, also the time when electronics was slowly, was just about to get revolutionized, right? So already some electronic computers were there in the 1940s. 47 was when transistors were developed, and this is after that when miniaturization started and electronics became important. But this is also the time when electronics was becoming sort of hot, like big computers were being made. So at this point, the people are also trying to model thinking in human or mammalian brains. So here is one very influential work in that direction. So they try to just come up with a model for the brain. And here is what that model looked like. It's a lot of complicated text here. But they say that every neuron, so the cells that make up the brain, they model it as a very simple structure. They say that it either fires or not. So it's like so this actually is true. So these neurons, so like the neurons that they do all kinds of things. I mean, they carry sensations, they're responsible for thinking. They seem to have this kind of activation, deactivation thing. So they're either firing or not firing. And this depends upon what is happening to nearby neurons. So they said, okay, let's take a very simple model. Each neuron is either active or not. Whether or not it's active at a time depends upon what has been happening to its nearby neurons in the just in the near past. And so that's what this is saying. So it's everything, synapses are connections between neurons. So it just depends upon what has been happening to its synapses. Synapses are just connections between adjacent neurons. Okay. Let's not worry about all this. The structure of the network does not change with time. So these neurons, somehow they are fixed. Their connections are not changing. It's not that the biology of the brain is changing. They're just firing in some different patterns, depending upon what the firing pattern is of their neighbors. And this can keep on going on for a long time. So they said, okay, let's try to model it let's try to model it like this. So again, some equations, but the same kind of equations. It looks very much like the Ising model. So there is a neuron these are whether it has some k neighbors. Let's think of k as 5 or something. Some 5 neighbors. Whether this neuron fires or not depends upon what these other 5 neurons, these k neurons, were doing at the last step. And how does it decide? It decides basically using a threshold. It sort of looks at some of the synapses might be excitatory, so maybe it is more likely to fire if that neuron was firing, and some of them might be inhibitory in the sense that if that my neighboring neuron, some neighbor I might have like the opposite affinity. If that neuron was firing, I should not fire the next time. So that is encoded by this J, again, just like the easing model. And then basically, if I have enough signal from the previous time from all my synapses, that neuron fires, otherwise not. That's the kind of model they had for one neuron. Okay. So that's the thing. And mathematically, this looks very much like, I mean, just pattern matching. Like if we were just these neural networks, we will see that this thing looks not so different from what is going on here, right? So the equations look very similar. And one of the sort of one of the things is one of these sort of truisms in physics is that same equations have the same solutions. So we sort of expect that that something similar as the magnet story should be going on here. But here it turns out that even just this one neuron is actually interesting, and it's called the perceptron. It was actually a pretty big deal in the 50s, 60s. People implemented it in hardware. We'll just see what it looks like. So what is this perceptron? So this is just the same equation written out, just slightly different. So think of what the neurons, these neighboring neurons are doing as a pattern. So there are k of them, there's 5 of them. Each one has 2 different states, either firing or not firing. So how many total patterns are there? Yeah, there's a quiz. So let's say there are 2 neurons, then how many patterns are there? Sorry? 4. 3? 4? Yeah, 2 raised to 5, 32. So 32 patterns are k, so 2 raised to the power k. So 2 multiplied by itself k times. That many patterns are there. And each pattern is assigned either yes or no. That is whether the neuron has to fire or not. Okay. So what we want to do is that we want to design a neuron which will fire in a certain way. So we have some yes or no answers in mind. For every pattern, we have decided that this pattern is a yes or a no. Right? Maybe it's something as simple-minded as that if at least 5 are 1, then fire, otherwise don't. Okay. So or at least 3 are 1, then fire, otherwise don't. Okay. Or it could be something more complicated. If an odd number of them are firing, then fire, otherwise don't. Okay. So those are the kind of things we have. But what we want to do is we want to design this neuron now. So we want to see which thing should be excitatory, which thing should be inhibitory, what should be the strength of those interactions, such that the neuron fires in a way that it detects this pattern. Okay. So this is the so-called perceptron problem, to design these J's and B's in such a way. Okay. So what we want to do is, now this is where the learning comes in. We want to learn this perceptron wants to learn the weights so that it classifies as many of these patterns correctly as possible. Sometimes it may not be possible to classify all the patterns correctly with just this. So in fact, the thing I just told you about the odd, like there are odd number of them, then fire, otherwise don't, cannot be done in this in general. But the other one that I told you, that if at least 5 are 1, then fire, can be done. And maybe as an exercise, you can try to see what the J and B should be. So the perceptron, what it wants to do is to, if at all it is possible, then it wants to find this J. If it's not possible, of course, it will not be able to find it. Okay, so this perceptron algorithm tries to do this, and the algorithm actually can be stated in just this one line. And this is exactly how we sort of learn, right? Maybe learn to ride a bicycle or play an instrument. If you have made a mistake, then change. If you made a mistake, if you ran into a pole while riding the bicycle, don't do that. If you don't turn the handle in that way. If you played a wrong note, then maybe move your fingers in a different way when you're playing the piano. So things like this. So this is how we learn it. And the perceptron algorithm does exactly that. So as long as there is a misclassified sigma, as long as there is some pattern for which my answer was wrong, then I change J slightly in such a way to make my answer maybe do slightly better on this sigma. Okay, I'll actually show you how this looks. Okay, in this video. So actually, let's just see that first, and then. So here is we are trying to now sort of train a perceptron, and on a very simple. This is a simple-minded data set. So this is has an interesting story also. It's like used in all kinds of statistics examples. So this is so someone went into a garden, and there is this flower called iris. If you're a student in school and in class 9 or 10, then you probably have done dissections of this flower. And what they did was that it has three different like sort of prevalent species. They are called Setosa, versicolor, and virginica. But let's forget about the three of them. Let's group the bottom two together, the orange and the green ones, and the top one as its own group. So let's say the blue is on one side and the orange and the green are on the other side. And they measured several things, actually just four things in this data: the length of the sepal, the width of the sepal. The sepal are the green parts, and also the petals. The petals I'm not writing down. We're just trying to classify a flower into its correct species based on the sepal length. So of course, if I give you this picture, you can probably very easily tell me, right? Like, so here there are some points, but maybe you can see that you can maybe draw a very simple sort of picture here, so that if some new point comes, then most likely it will fall on one side of whatever you draw, depending upon whether it is a blue one or a green or orange one. So what will you do? Well, yeah, but yeah, right side, yeah. So there's some side kind of thing, right? So maybe if I draw a line like this, then I can say that if I get a new point, if it lies on above the line, I will call it Setosa, and if I lies below the line, I will call it this. That's what as a human I would do. Now we want a machine to learn that, and we wanted to. So we'll see that the perceptron does actually succeed in learning that. So this is a video of the perceptron algorithm in action. So what is it doing? So it is basically these crosses that you are seeing are the examples where it is sort of wrong. So it is trying to move a line. Right now you can't see the line because the line is actually right now very far away. It is completely wrong, but slowly the line is coming. So that orange line, this pink line is the line. Each time it sees an example, it tries to adjust the line to do better on that. Let me speed it up. It doesn't actually take this long. This picture is not drawn to scale in time. So now, but you can see what's going on now. It's almost succeeded. There are just these few annoying examples there, and but it is doing so. There's something important here. It is slowly changing. It is not like it has seen an example, so it just moves the line a lot to make that one correct. Sometimes it does that, but then it tries to recorrect it back. So it is looking at all the data, but for every single piece of data, it is only making small adjustments. It's not committing to doing that one correctly at the expense of everything else it had learned in the past. This is important. Okay, but then eventually it does succeed. Maybe I'll speed it up more. Yeah, so it's almost there. Yeah, so eventually it does succeed after having looked at all the data several times. So it's like it has to do this revision before the exam kind of a thing. And but then it is also has to be slow. It doesn't have to sort of like just because it has seen some new example, just forget everything it had learned in the past and just do this example correctly and forget everything else. So it changes slowly, and then after a while it does get the correct thing. It's almost done now. Yeah, that's the thing. So it stopped at some point. So the perceptron, and by the way, this algorithm, yeah, right now it's trivial to implement, but it was actually implemented in hardware in the 50s. Books were written about it. It's an important algorithm. It can be generalized in several ways. In some ways, it was actually the leading machine learning algorithm till about 15 to 17 years ago. I mean, in a more expanded form, under the name of support vector machines. Until neural networks took over. But neural networks also can be seen as just perceptrons on top of each other. We'll see that in some way soon. But other than that, it also anticipated two very important rules of thumb of modern deep learning as well. Okay, so here are these two rules. Actually, they are the same rule written twice, and this rule can be researchers are saying be slow. So you consume data slowly, but you consume all of it. You do not make very drastic changes. You're learning, so you have seen all the data several times. So you have learned something. You see some new example where you're making an error. So you don't just forget everything and try to do this example correctly. You make maybe small adjustments to maybe reduce your error on this uh, on this uh, on this example. So that's so these two rules of thumb still continue to be important. Uh, like quite a lot of machine learning research is actually to just get properly implement these rules of thumb. Okay, so any questions so far? The last two things have been slightly heavy. So any questions about the notation, about the names, about the history? Yeah. Yes. 50s. Sorry. Yeah, so it was implemented in hardware, like actually in analog. So like some of the implementation was actually analog. So it was like you literally, yeah, you could do that as well. Yeah, I mean you'll do punch cards all maybe, but 10 years later, at that time you're probably just not maybe doing some things on some what is it? It's called these variable resistors where you yeah or capacitors. Yeah, so like so at that kind of thing. So uh, so the job of a program. So okay, so yeah, maybe one more you can have this joke. So computer used to be a not a machine but a job description 100 years ago. A very well paid job would be the job of a computer, which would be a person whose job to compute, and this was like not a trivial thing. And programmer at this time in the 50s did not mean like clicking on a keyboard, but yeah, going into a big room full of triodes and things like that, and adjusting capacitors and resistors. So yeah, so at that time also these things were going. Okay, so yeah, so the point is that okay, so with one perceptron we cannot do much more. We can do this simple things like this flower thing, or as I told you, even this thing about checking odd number of ones or not cannot be done with a single perceptron. So the important thing is that you need to connect them into a network. Okay, so this is where the networks come in, and this is where one of our first of the laureates enters the picture. So there are these two papers, one in 1972 by Shunichi Amari, another in 1982 by John Hopfield, who is one of the laureates. Both are mentioned in the Nobel citation, where what they did is the following: they showed that if you connect these perceptrons in a network, they can remember quite complicated patterns. And what does it mean to remember? So what it means to remember is the following. So, so what you want to do is this. There is some pattern. Let's say this particular pattern: minus, minus, plus, minus, plus. So this is our pattern. We want to remember right now. Just say one pattern. What we want to do is to adjust. So we are back to our easing world and these J's and so on. So now, so we can think of each of these as an individual perceptron, and then they're connected in a network like this. And what we want to do is to adjust these interactions between them so that they remember the pattern in the following sense. If I now feed into this network some slightly corrupted pattern, right? So maybe I change one of the minuses to a plus, okay? And then what this network should be able to do is to maybe make small adjustments, very mindless adjustments. It should not be able to say, oh, this is the pattern I remembered and that's why I will make this adjustment. No, it will do something very local using just these J's, such that it slowly or reasonably quickly, slowly but reasonably quickly, converges to the pattern that was actually stored. And they show that this does happen. So the point of these two papers was that in very related models of these connected perceptrons, it does happen that you do the following: you for a given pattern, you find some J which minimizes the total energy, which is like the total dissatisfaction, as we were saying. And then what you do is if you fix this J and that you initialize the network in a slightly different pattern, which is not too different but somewhat different. Then what all the vertices do, all these sort of all these participants in this network do is that they repeatedly apply the following. They locally try to minimize their energy. If they are dissatisfied, what the only thing they can do is flip their view. So if they were plus, change to minus, the minus change to plus. That's the only thing they can do. They do that. They just do that. If they are dissatisfied right now, they just change that. So if their energy is sort of positive, they will just try to make it negative. So negative energy is like, yeah, this is some maybe strange physics thing. Negative energy is being satisfied. Positive energy is being sort of frustrated. Why? Don't ask me. I mean, that's and yeah. So and then if they keep doing this, they slowly converge to the stored pattern. So their models were slightly different. Doesn't matter the technical difference, but they both got to this point. Okay. That very simple dynamics. Each one is just locally trying to minimize its own energy, minimize its own dissatisfaction. It converges to what was stored globally. The whole system globally converges to the global storage. So this is important. There's small parts of the network. They are doing very simple things, but together they are accomplishing something that looks much more impressive. Okay. Okay. So this was something. So at least you could remember one pattern. Okay, and then this was refined later. But remembering one pattern maybe is not so impressive from the point of view of applications, right? So, like the example is that if I tell you that I have a very nice shiny new machine learning model, and it will always recognize this 1 0 I drew yesterday, but not everything else. It will say no, this is not the 0 I drew yesterday. But if we give it exactly the same 0 I drew yesterday, it will say yes, this is the one. This is not so impressive. What would be more impressive is if it can recognize a 0 that is drawn by any person who, say, let's say, writes in Devanagari, Hindi or Marathi or English, right? So those zeros look the same. If any, but they will not look all exactly the same. The pixels will be different. If I draw a 0 now, and then even the same person will draw a 0 within like 5 minutes, it will look slightly different. As at images, the pixels in the images will not be the same. But if the model can recognize that, that will be more impressive. That will also be more useful, because one of the first applications people are trying to do with this is to recognize things like pin codes on handwritten envelopes. Okay, so we'll see that that can be done quite easily now. So the one big idea here that people came up with was that you want to do not just recognize one pattern, but many patterns. They are sort of related, but not quite the same. And this was done by saying not just that the lowest energy configurations, so the highest, the lowest dissatisfaction configurations, but you say that instead of that, I will let the model sort of wander around in some of the low dissatisfaction configurations, not just the lowest one, but a few more, maybe a lot more. But all of these have small dissatisfaction, not too much higher than the lowest. That is the important thing. Okay, so this in statistical mechanics has again been known for a long time. What you do, you sort of think of the system as being at a temperature. So if you have no sort of heat available to you, if a system has no heat available to it, the only thing it can do is getting no external energy. So it will sort of, in many situations, it will just go to the lowest possible energy state, stay there. If it has some heat available, say some positive temperature around it, then it can sort of play around a little bit. It can be slightly dissatisfied because it has some energy coming in from the inside to raise its energy. So that's what they did. So they said, okay, what will happen is that there will be some so-called probability distribution on patterns. This will depend upon how far the things that are far from the lowest dissatisfaction will have lower and lower probabilities. So they will be less and less likely. And things that are close by will be more likely. But of course, but it also depends upon how many of those there are. So this so-called entropy comes in. So I would not go into a lot of detail about this. The issue is that even this is maybe too regular. Like this has been studied in physics, might be too regular to capture everything. And what Hinton was our other laureate, one of his main contributions, was to come up with a method to solve these two problems in one go, and using again a very simple kind of idea. The idea is this: so far everything we have been doing, everything has been visible. There is this network, it has these nodes. Everything is, all the computation it is doing is all on these visible nodes. You put all the data on those nodes. It does all its computation also on those nodes, and then it spits back the answer also on those nodes. This is not how you do computation, even by hand, right? It's not like if I give you a sum, like I ask you to multiply two numbers, I write down 10 digits and another 10 digits. You will actually write down a big multiplication sum, then write down some 20 digits. But in the middle, there will be this large chunk of computation that you have done that you will not show me necessarily. You just give me the final answer. But it's important, and this is again one of the things. It seems like a very like almost a like a foolish thing to say, but yeah, it's sort of it turns out to be fundamental that computation does require space. It requires more. It requires not just the sort of the space required to write down the input and the output. It usually requires more than that to actually do the computation. And this can sometimes be rigorously proved that some computations do require more space. So what Hinton did was to show that, yeah, well, let these models do this hidden computation. Let's give them more nodes, not just the nodes that are part of the input and the output, but nodes that are in between as well, which are hidden in the sense that they are not part of the input or output. The model just does some computation there, and then after that, the output is given out somewhere. So it's giving it working space. Okay. So this again, in usual algorithms, this has been known for a long time. You need memory to do the computation. You can't just do anything without memory, or doing it by hand. You need paper, pen and paper to write. So this idea of having hidden nodes becomes important. For the technical reason is that now you allow a much richer class of probability distributions or likelihood, unlikelihood patterns. So they are not as, so I said that that these might be too regular. So now these things are not, that these kind of distributions that I was writing down might be too regular. Now with these hidden nodes, they are much more powerful. They're not as regular. They can do more things. They can encode more situations. Okay. But this power comes at a cost. The cost is that in the end, we want to do learning. We want to learn what these interactions between these hidden nodes, the output nodes, the input nodes have to be. I mean, it's not sort of God given from above, right? This is the whole point of this is to do learning. This learning process now becomes much more complicated. Okay, in these things. So let me at this point show you a picture from the Nobel Academy where they did a nice picture of comparing the three things I've talked about so far. So this is Hopfield network, the Amari Hopfield network, where there was just some very simple network with nodes, and like every node was connected to something, and they were just doing very simple dynamics. Each one was just checking how many of its neighbors are in a certain state, doing some local computation, updating. Then came this so-called Boltzmann machine. This is the thing with the hidden nodes and everything connected that I showed you. And then this thing that I did not show you, something called restricted Boltzmann machine, where what the only thing was that you say, okay, there will be these hidden nodes and there will be these output and input nodes, but we will not connect everything to everything else. We will make the connections more sparse in some clever way. These sparser connections, fewer connections, they are still somehow connected, but not too well connected. And what this would achieve is that it will make this learning process more computationally tractable. That was so this computational tractability is also an important thing. In the end, these things have to be implemented on a computer. So you also need to make sure that these things work well. So this restricted Boltzmann machine was also invented by Hinton and collaborators. The issue with this is that it's not. It's like it turns out to be still too complicated. So it's not used so much these days. What are used these days are something that are inspired from it, but in some sense even simpler. So this is what a typical neural network today looks like. Don't again worry about the notation. What is happening here, that each of these rectangles that is drawn, you can think of it as just a collection of perceptrons. So these are each rectangle is just, think of it just as just one line of perceptrons. And what is happening is that the perceptrons here are taking as inputs the outputs of the perceptrons here. Okay, so the many neural networks today look like basically a chain of like you have perceptrons arranged in sort of a grid, like horizontally and vertically, and the perceptrons at one level feed into the perceptrons at the next level, which feed into the perceptrons at the next level, and so on. So what are these numbers 100 and 400? So maybe here you had 100 sort of like, so remember in our flower example, we had two numbers, right? The sepal length and the sepal width. But in a more complicated question, I might have more numbers describing each data point. So that 100 is how many numbers do I need to describe each of my data points. Then this 400 here is how many perceptrons do I have here, like at this level. So I have 400 of these. Then 50 on this, then 80 on this, and then 10 on this. So that's the kind of structure that looks like. Okay. How do you train such a thing? So okay, and by the way, again, the important thing, the hidden things are there. So all of these are hidden. The input is given, the output is given here, the input is given here. These things are sort of for the computation of the network. So this is the part that came from the Boltzmann machine idea. The restricted Boltzmann machine idea is that the connections are only from one level to the next. It's not like that this perceptron is also connected to this one. They only go in layers. And this simplifies matters a lot. Okay. So let's see, I have 10 minutes. Okay. So the way these things are done, and I will maybe it will become a bit technical, so I will not go into details, is actually in some ways not so complicated. Mathematically, it looks maybe a bit strange, but what you do is you say, I will try to, so I have some inputs where I know what the correct answer are. I try to see for any collection of the parameters of this perceptron, what is my current error? That's the technical term for that, for some reason, is loss. So how big is my loss? How much error am I making right now? And then I compute something called derivative, which is basically just a measure of, if I change my weights slightly, how should I change the weights so that let's say if I change the weights in a certain direction slightly, how much will my error change? This is what the derivative is. So you find out this so-called derivative or the gradient, which basically tells you which direction should you move the weight in to slowly decrease the loss. So your goal is to decrease the loss, decrease the error. So that's called gradient descent. So you try to now move the weights in such a way that your loss decreases by a little bit, and you keep doing this again and again and again. Okay, and that is it. So the only question that is left now is how do you? So by the way, so how do you actually compute this gradient? This gradient, if you remember your class 12, is like you might have seen something called a chain rule. That's what goes on. It's just the chain rule. Funny thing is that one thing that becomes very important here is how this is the chain rule applied. So I will maybe not go into the details. So the chain rule can be applied in forward or reverse. If you remember your class 12 calculus, then think of applying chain rule to f of g of h of x. You can either start differentiating from the left or from the right. It will give you the same answer. Which one you use actually seems to matter. It turns out to matter a lot. The forward mode is to go from input to output. Sorry, what happened? Yeah, forward mode is to go from input to output. The problem is that this causes a lot of the intermediate results to be too large. This space I was talking about for this computation. So this computation that is going to happen during learning is too much. It turns out that the so-called backward mode, which is to do it in the other way around, which is slightly counterintuitive, is much more efficient. It is like, yeah, so it's much more efficient. And then the question arises, who invented this reverse mode? It seems like a very obvious thing. It's actually not so obvious. And again, it's so fundamental. It is invented in many fields for different reasons. It was invented. So this Wilkinson's thing, I think, is in chemical engineering, so some plant design kind of thing. Other early work was in electrical circuits. Then there are people in numerical analysis, which is like people trying to do optimization and seeing how much error in your data will cause how much error in output. And then there are also people in mathematics and theoretical computer science doing this. And there also turns out to be a close connection to something called backpropagation. Backpropagation is just actually another name for this reverse mode automatic differentiation. It was popularized by another paper of Hinton, one of our laureates. That's a very suggestive title, Learning Representations by Backpropagating Errors. So the point is that there are errors. You want to remove the errors. So what you do is you try to figure out by sort of backpropagating the output down to the input, how much should each weight change to reduce the error slightly. So that's sort of, you can think of it as a slightly different philosophical interpretation of reverse mode automatic differentiation. This paper also did something, another interesting thing, which continues to be a very active and unsolved kind of problem to this date. I gave you all these pictures of networks with like layers and so on. Very quickly, it becomes hard for a human to judge what is this network actually doing. Maybe it's solving this problem, but how? So, for example, we don't know how to explain what AlphaFold is doing in some sense. I mean, we have some, of course, there's some intuition because like that's how it was designed. But probably even the designers cannot predict that if I change this thing slightly, how will the performance increase or decrease? The only way to figure out is to do experiments. So we would want to be more explainable, more well understood at a fundamental level, like I mean, like the way many other parts of physics are. Like for circuit design, for example, right? You can usually figure out if I remove this component, what will happen. We are not at that level here. And so what this paper was doing is something on that line in a very simple problem. It's just this is their full network for some question. The question was to detect mirror symmetry. You write down a pattern, is it mirror symmetric? And they were trying to see what is each node in the network learning. Is it learning some special feature of the problem? And they were trying to do some kind of like neuroscience on the artificial neural network. So that's quite exciting. I mean, it still remains open. I mean, like this, for this simple network, it's fine, but in general, to do this still remains open. Sorry. Yeah. Okay. And so this reverse mode AD is sort of important. It's available today as an important component of packages like JAX, TensorFlow, PyTorch. You can use them. I intended to show you an example of how simple it is to write non-trivial looking things. And this training of these so-called large models will be sort of inconceivable without this simple reverse mode automatic differentiation idea, or what is called a cheap gradient principle in numerical analysis. So this is actually a nice essay. It's a history of mathematics kind of essay. If you search for it on your favorite search engine, you should be able to get it. It's quite nicely written. It's like also a work of literature in some. Okay, so with that, I will just end. So here are these networks. But maybe before that, let me just show you one example. Like this is like something. By now we do it in the first class on machine learning, just to show you how simple these things actually are to play around with. So what we are trying to do is to detect digits. So there are like pictures of digits like this that people have drawn. By the way, what is this digit? Okay, okay, yeah. So this is supposed to be 5. So maybe someone will ask, okay, you drew 5, is it 5? Yeah, and what we want to do is to train a network to take these images as inputs and say, is it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these pictures can look somewhat, so some people have good handwriting, some people like me have atrocious handwriting. So, okay, yeah, so there are like good ones. Here I don't see anything atrociously bad, but you will see a few. This one is probably a bit on the bad side. This one is also, it looks like a delta to me. But yeah, so the network is supposed to learn to classify as many as possible. So what you do is, so this is the typical way a machine learning thing works. Okay, so in this case, it turns out that, so one big thing is to actually get the data and clean it up. Clean it up in the sense that, make it sort of uniform, that it can be fed to a machine properly. So this has already been done for this data set. This is a very well studied data set. So this we just get for free, more or less. So this part is doing that. Important thing is that whenever we are doing something about learning, we want to see that we are not fooling ourselves. So this is like, maybe I prepare for an exam and I go and get a very high score on the exam, but all my learning was just for the exam and not really for what the exam is for some subject. I didn't learn anything about the subject. I learned enough to just sort of get good score in the exam. That should not happen. When new tests come in, I should still be able to do well. So to do that, what you do is that when you're doing this learn, you keep testing the model on some data it has never seen to see what is its real performance. Not just on the things that it is being trained on, what it has seen, but you then check it. Okay, what is your score on this new thing that you have never seen? And then finally, when you are done, you again check it on something that is different from all of these two things. So these are called validation and test. So validation is the part that when you're learning, you keep checking to just check progress. And then at the end, maybe there's some final whatever capstone exam where you're shown things that you have never seen before, and you should still do well if you have actually learned. So that's the point. And so here is what. So these are all just to plot these pictures. The actual code of the model just looks like this. It's just this 14 lines. That's the model. Okay, so this is it's like one of these layered models with just 2 layers. I will not go into the details of it. Looks like the actual picture looks like this. So the images are 28 cross 28. It goes into 1 layer and then finally 1 output layer. I just did this this morning, so I will not bore you with it. It takes about few seconds to run. You can see how it is doing. So there is some accuracy. You can see it's actually doing quite well. It has learned to do very well on the thing it was learning 99%. But there's some surprises, and these are surprises that. So this is the thing I was talking about. This is the thing it is training on. It has the accuracy is approaching 1. It's getting 100% score on that. But on the things that it has not seen, after a while, it is flattening out. And this is a phenomenon you see again and again. This is a question of overfitting for the exam. You have learned too much for the exam, but like on the real world, your performance is now plateauing. You're now learning to ace the exam rather than the actual subject. And this does happen. This is not just a joke. This does happen, and one has to protect against it. That's the reason for doing validation. So ideally, you just stop once, because in more catastrophic things, you can now start dropping also. You can start fitting to things that are, you can sort of start seeing patterns that are not there, which are just sort of there in your training data. So this is just the same thing for loss also. You can see the error is sort of decreasing, but on the training data, but on the validation it can. So yeah, so with that sobering thought, let's end today. Yeah, maybe I want to show. So like okay, so it gets good prediction even on the the prediction on the validation is also not bad, right? 97% more than 97% score. So I just try to see what kind of things does it get wrong. So here are some questions, some things it got wrong. So the correct answer is 8, but it claimed that it is correct answer is 1. It claimed it is 8 with a confidence of 87%. Maybe not excusable. This one maybe is more excusable. The correct answer is 3, and it said it looks like a 9 with a confidence about 43%. So yeah, so these are the things it got wrong. Like you can see that they're all from the Hall of Fame of bad handwriting, most of them, not all of them, but yeah. So yeah, with that, let's stop. Thank you.
Take a break for chai, and before we take a break for chai, then of course we'll come back and speaker will be available for all the questions. So let me announce the upcoming sessions. The next session, the third Sunday of this month. So the third Sunday of this month will be at Ruparel College. It will be given by Bihan Banerjee on exoplanets. This month has 5 Sundays. So the 5th Sunday will let you know. It will be live from a lab. And the next month session at Prithvi, that's on 5th of Jan, will be by Professor Subir Sarkar. And it will be again a talk on cosmology. And so these are for the upcoming sessions. So we'll end the live stream now. Take a tea break and come back and then you can ask questions. Thank you.